My name is Bojun, and I'm going to talk about Attachable Sanitizer. I'm working for LG Electronics, and I'm totally interested in memory leak problems. In this talk, I will tell you about the motivation and solution. First, let's check whether memory leak problem still matters in C++. This is the table we've seen before. Do you remember? Mm-hmm. Yeah. This is an opening keynote. Then, thanks, Anastasia. Anyway, and here you can see that memory leak problem is still major frustrating issue in developing C++. So, it is obvious that using smart pointer correctly, then there will be no memory leak caused by unreachable memory. But sometimes, and some people may use raw pointers and smart pointer incorrectly, or sometimes you need to use C library. Let me show you one example. This is just two-line patch from TensorFlow project, and TensorFlow project is a very famous project, you know. And here you can see that it was using raw pointer. And this is just two-line patch, which means it seems like there was a memory leak. And now it is fixed, by the way. So here I want to say is that memory leak problem is inevitable issue, even for expert C++ developers like you guys in here. So let's talk about some existing memory leak detection tools and limitations. If you have ever fixed memory leak problems before, then you must have heard of Valgrind or address Sanitizer. They could detect memory leak as well as other issues. But because of the ability to detect other issues, they are a bit slow. So if you want to detect memory leak only, then Leak Sanitizer is recommended to be used because it is not slow. And Leak Sanitizer works like this. So first, the target program calls the memory allocator functions like malloc, calloc-free kind of things. Then it is hooked by preloaded LSan library and is save and delete allocation information. And then on process exit, the LSan library analyze and report unreachable memory. So I can summarize like this. LSan library is preloaded on target process starting and hooks memory allocator function, save and delete allocation information, and then analyze and report unreachable memory. Leak Sanitizer is a very good tool, but it has some limitations. The limitation number one, it needs to test again. This is a sentence I told you previously that LSan library is preloaded on target process starting, which means you need to restart the target program to use Leak Sanitizer. So you need to test again. The problem is that if you want to test again, you need to know the scenario and you have to perform that scenario again, and both of them are not easy in some cases. For example, like a field issue, and that it's almost impossible to get the scenario. And for example, like a test issue, even for test issue, then it could take a very long time. The limitation number two, it reports only on process exit. So this is the figure I showed you before, and if you apply LSan to the daemon or service, like it never exit, then you cannot get the report. The limitation number 3 is Heisenberg. Here you can see that LSan library is loaded on the same preloaded, so it's running inside the same. It's running together with the target program. It shares the virtual memory, so it save and delete its allocation information that will affect the memory, and that could decrease reproduction rate. So I will tell you about the solution, and solution is in fact an attachable sanitizer. And attachable sanitizer uses eBPF and uproof, so I will tell you about this first. eBPF is a virtual machine that running inside Linux kernel. So it allows user-defined code can be run inside Linux kernel. It is a very powerful feature. So thanks for its powerful feature, it is used in networking, security, observability, tracing, kind of things. And there are lots of projects like BCC, Selenium, and so on in user space, and some for kernel space, like many modules are working hard to support these features. And there's a BCC project, which is one of the most famous open source project in this community. And Attachable LSan is implemented based on this BCC project. And uproof. Uproof is a kernel feature as well, and it provides dynamic tracing for user level applications, which means you can hook user function with this feature. So there's a main function is calling foo, and you can see that main function is go to the foo function like that. And if you attach uproof to the foo function, then it can hook its execution and do something else right before calling foo. So you can use this feature, you can make eBPF application. This is kind of some typical overview of the eBPF applications. So eBPF application composed of 2 parts. One is eBPF program part, and the other is eBPF analyze and report part. So first, eBPF program will be compiled and loaded to the Linux kernel. And then attach uproof to the target function of target process. And then if target process calls this function, it will be triggered the eBPF program that is loaded, and that eBPF program will save information as it wants. And this analyze and report part could read the saved information and do analyze and report whatever it wants. Okay. To use this feature, it needs 2 things. First one is, okay.
I was just wondering if there are any limitations on the kinds of functions that can be hooked. Like, does it have to be like a dynamic symbol? Like, it works well for the allocators either way, but I'm just wondering, like, if you have like a statically linked function or something that potentially gets inlined, I'm just wondering if there's limitations on what you can hook.
In fact, there's no limitation, because uproof is hooked by some instruction point, so there's almost every point, every function can be hooked, because the argument to given is the file name, I mean the address of the location of the instruction, and address of the location of the instruction. So it can be hooked by any point of user applications. Yeah.
So actually, you cannot trace two types of functions, inline and non-traceable.
I didn't hear you.
You cannot trace inline. You cannot trace inline functions.
Oh yeah, sure.
You can also not trace non-traceable functions.
Yes, yeah, you're right. It's only for the inline function cannot be traced because it is already inside some functions. Okay.
So inline like with keyword inline, or inline what compiler has inline with O3 optimizations, for example?
uproof is just attached to some location instruction address. So it depends. So the output, it depends on output.
So for example, if we compile something, we can still, even with optimizations, we can still generate some sort of symbol file like for debugger.
Yeah, you can do that, but uproof can be attached only for the location of the address. So
Okay.
so it cannot. If it is inline, then it cannot be.
Yeah.
Yeah, maybe some debugging information is, but it doesn't matter for this feature.
Is there some overhead? I mean, if uproof runs in the process?
Yeah, sure it is. Yeah, it's using kind of system call. It raise exception and go to the exception table and do something. So kind of thing. So if it triggers, then it means it. You can see that it's going to it switched to the kernel mode. Kernel mode. Yeah, user mode becomes to kernel mode. Okay. And first, but it is because of this powerful feature, it needs some requirements. First one is root privilege, and the second is kernel configs to enable like uproofs and to enable BPF. Oh, it's anyway. So, but it is enabled by default for major Linux distributions like Ubuntu. Yeah. So now let's talk about attachable LSan. So attachable leak sanitizer is eBPF application which hooks memory allocator function, save and delete allocation information, and analyze and report on each of the memory, which is same as LSan. So this is how it works. So it composed of two parts. This one is eBPF program part, and here is analyze and report part. So it is compiled and loaded to the kernel and attach uproof for the memory allocator functions like malloc, free, calloc things. And if target program calls memory allocator function, that it will trigger eBPF program. And here it saves allocation information and delete. And then it can read the saved data and analyze and report unreachable memory. You can check this one first. Here you can see that it hooks on running process, so it can start tracing dynamically. That's the first one. And second, the allocation information is saved in kernel space. You can see this one, this bar, and this one is kernel space. It's a kernel memory, by the way. So it doesn't affect the virtual memory of target process. And it can analyze and report as a different process. So it can do it as it wants. So you can report not only on process exit, but anytime you want. So I can summarize like this. It is attachable and not affect user memory, and report at whenever it wants. It's only for Linux and need kernel configs, and it needs root privilege. So now I will show you some demo. I prepared 4 demos. The 2 is for examples, and the other 2s are actual open source cases. First one is simple example. Here I will show you that the attachable Sanitizer detects leak as original Sanitizer does. So here's an example code that very simple. Main function calls foo and foo bar, bar buzz, and buzz calls new. If you want to use Sanitizer, you can compile with this fsanitize leak, and then you can just run it, then you can get this report. This is original Sanitizer report, and here you can see the main function calls foo, foo bar, bar buzz, and operator new. And I changed the test code a little bit because attachable LSan can detect leak for some kind of daemon. So I add some infinite loop and sleep 5 seconds for each loop and call foo and foo bar, bar buzz, blah, blah, blah. Okay. And just compile it and run it. And then sometime later, I attach attachable LSan to that process. And here you can see that sudo means it needs root privilege, and you can see that it reports as LSan does 4 bytes directly. And as I told you, it can report as it wants, and so I implemented to report and for each 10 seconds. So it report again and again and again. It could. So you can see that allocation is still happening in that process. So you can see something like this count is increasing. So here's a quiz. Can you find something weird in this report? There are 3. Okay.
Mangled names.
Okay, right. Correct. There are 3. Unknown, right, exactly. And the most difficult thing is remain.
The stack ID, maybe?
Stack ID? Stack ID is not, in fact. In fact, I have to remove that.
So, like,
NW.
so my idea is like we kind of trace at our interval not how the program sleeps, so we might get not the right increments of memory leaks basically, because we leak every time 4 bytes
Yes.
or something, and here we have like the next number 12.
Oh, yes, that's because it.
Yeah, okay, it's like 3 intervals have passed.
Yes, yes,
If
exactly.
it's not multiple of what we sleep, for example, then we can allocate like next time 14 or something if this program would call more often.
Yes, that could be.
Get into the middle of the cycle, basically. Yeah, but I'm not sure if it's a.
Yeah. Yeah, you're right. And I will show you some hint. Here, main calls foo, foo calls bar, bar calls buzz, and buzz calls new. Okay, again.
Yeah, we're missing Baz.
Yes, exactly. Buzz is missing, right? Yeah,
How does this tool determine that the address is not reachable anymore?
pardon?
How does the tool determine that the address is no longer reachable?
I mean,
don't think it
So
does.
if the memory leaked for 10 seconds, maybe the address still lives somewhere and 20 seconds later we'll use it. So how do we know that it's unreachable?
I understand. I will finish, okay. I will tell you that first, okay. Okay.
So the output does show the real memory leak and
BPF
not just something that can get freed like after 10 seconds.
I didn't hear that, sorry.
So the output here, I mean, if something is shown like a memory leak, then it's a real memory leak, and not that something can be suddenly freed like by something else, like after 10 more seconds.
I can get what you're talking, but this report is for unreachable memory. So unreachable means you don't have pointer to pointing out, so it can be possible. But if it happened, that it will be bug, right?
Yeah.
Yeah. And this is how we analyze unreachable memory. And I use the same algorithm with LSan does. So, okay, LSan. So I will explain that how LSan does. So LSan considers each heap allocation as tree node and traverses the tree from the root. And the root set is 4 things: global variable, stack, and general purpose registers, and thread worker strategy kind of things. So stack means this one kind of things, and global variables like this. So just mark every node as unreachable and traverse from the root and mark it as reachable, like this, yeah. And then traverse from the heap and mark it as indirect link. So this is how they distinguish unreachable memory. It's same as ALSan does. The algorithm is same as ALSan does. Attachable ALSan do the same algorithm with original ALSan. Yeah.
LSan is an instrumented code, so it knows which addresses are pointers and which addresses are just values or whatever. How does PPA, without instrumentation, how do you know like which addresses to traverse?
First of all, ALSan does instrument.
Yeah.
As address sanitizer do.
Yeah.
Linux Sanitizer doesn't. Linux Sanitizer just library preloading. Oh. Linux Sanitizer doesn't do that.
Doesn't instrument.
No instrument, just preloading.
But even ASan reports only at the very end.
Pardon?
Even ASan reports leaks only at the very end because
Yes.
there is otherwise no way to know what is truly leaked. But there are lots of ways I can stash away an address. So ASan reports at the very end.
Yes, I know that. And address sanitizer do that either, but in fact, I didn't analyze the address sanitizer, but I analyzed the Linux Sanitizer, and Linux Sanitizer doesn't change the target program at all. It just library preloading,
But it also reports at the very end.
Yeah, it report it, and there is a question that which one is the pointer or not. How do they distinguish? That the answer is that they don't distinguish. They just assume that they are all pointer. Just assume. So
every 8-byte
yes.
block, is it a valid pointer to anything?
Yeah, consider to pointer and go and check whether that memory is available or not. Yeah.
Sounds slow.
So
What if I store like indexed addresses? So for example, I store a pointer not to the beginning of the block, but let's say 8 bytes into the block, because I have some hidden data in the blocks. So all my pointers are actually not to what I allocate, but 8 bytes in.
oh yeah, I understand. It cannot be detectable. Okay, that will be classified as unreachable. Yes, you're right. That's why we cannot have some kind of garbage collector in C++, like native language. You're right.
So just last question: is it possible, like, to detach the program afterwards from the process, like, to attach, observe what's going on, and then to detach, and let the process run like?
Yes.
Yeah.
Yes, exactly.
It's possible.
Yeah, it's possible. It's just after I quit, then it just becomes normal. Yeah, becomes normal.
One thing I'm wondering about as well, so it seems like when the program's running and it's been attached to, like, we hook into all the global allocator functions so we can track all of the allocations that are being made. But like, when do we actually walk the address space? Like, does the, like, and when you're doing that, does the program have to be suspended? Like, is that, I guess I'm just kind of wondering, like, when we actually generate that report and we walk from all of the global pointers and everything, where in this process does that happen, and does it require suspending the process?
Yes, this point.
Okay.
Yeah, and this point, it is splitted on, it is another, I mean, this is not target process, so it can run as it wants. But in fact, I have to say that I said the root set contains other things but register, and if you want to get the register, you have to stop the target process. So I implemented to do that, but it will slow down very much for target program. So
Right.
it is not default option. It is, you can enable, but it can slow down the target program a lot.
So like the eBPF program itself, like whenever it checks, it kind of snapshots the process at that point.
Yes,
and collects
yes.
all- Okay.
Yeah, yeah.
Makes sense.
It doesn't snapshot, just go and read it. So it can be, the report can be wrong. I mean, because during it is running, so
It's
but
still running.
yeah,
Okay.
it's still running. So it can be wrong, but it is report periodically. So if it is first alarm, that it will be removed soon.
So question, so let's say I make a malloc, you trace it, you write to the map, and then you report. So you don't see a free, right? I don't call it yet. So the report will tell you that the leak, but actually I will call free later.
No.
No, I think he's saying it does actually like check from the roots and actually really do reachability analysis.
Well, the program is still running, right?
Yes.
Like I don't call
Just,
free,
it just maps its
I
memory.
report.
Yeah, but
So in that case, you don't know, like you don't trace the free.
it does know, because it tracks like unreachable addresses which were allocated before.
It doesn't check for whether you actually freed it, it checks for whether you could free it. As long as you hold a pointer to it, you can still free it in the future. So there is another error where you hold a pointer, you could free it and you never do.
Mhm. But
That's,
that's potentially.
yeah, so that's not what it does.
Yes, that's, in fact, I said this tool is to detect the memory leak caused by unreachable memory. Yeah, so this is it, and there is another tool to do that. So kind of things that reachable but kind of leak. Yeah.
Is this open source? Out of curiosity, this is fascinating. I'd love to play around with it.
I opened it. Yeah, so you can. I will tell you how to download it and build it at the end of the talk. Cool. Okay. Okay. So this is where I am. Okay.
I think we were talking about the fact that Baz was missing.
Yeah. Right. So I report it to the open source community, and it turns out it is not such a simple issue, and there was some solution has been suggested on Linux Kernel about 2 weeks ago, and I applied this solution, and I can get this buzz line. Okay, here's a simple example case, and next, long test case example. Okay, can you find something weird in this example? Pretty simple. Not weird bug, I mean.
Where is n and m defined?
Yeah, m is just, I skipped, but
You'll eventually overflow your log.
exactly, it will overflow. Because if sand comes, then it's just increasing, so it will overflow and crash this data array. And if it contains some pointer of heap, which is allocated pointer of the heap, then this stack overflow will cause memory leak, right? And it will happen only after send function is called more than n times, in this case, million times, right? So, which means if you want to use Sanitizer, you have to wait until that million times of send is called, and then the report will be, and then you can get the report. But if you can use attachable Sanitizer, then you can just apply it and you can get it. But that should be, the assumption is that it is already past a million times anyway. It always happened after.
Yeah, but
Yeah.
even once the data array gets corrupted, it gets corrupted with the addresses to the heap area, right? So again, so the addresses are still reachable, just not by the CppNow semantics, right?
No.
So after I call the send n+1 times,
Yes.
then the string is placed inside the data array, but it's still there. It's placed there.
Whatever data was pointing to is now unreachable.
So-
Yeah, exactly.
It's the old pointer that was
The
over.
internal string pointer will be lost.
The string itself is fine. It's the int star.
Yeah.
So you have some int star that points to something, and that something is now unreachable. So there's no way to free.
so the
Data,
So
data,
so-
yeah. It will be
I
crashed.
see. So some of the m pointers to int will get will start leaking.
Yeah.
Yes,
It's not the
exactly.
Strings are fine.
The strings are fine, right?
Okay.
So, but I make an actual example. The example I show you is everything is actually runnable, okay? Except this one. So here's a code, a similar code that there's a log. I changed it to just the int, and a data array, same as, and let's consider it takes, I use millisecond for me to test, but it can be second or hours anyway, so it can take very long time, and then you can get the leak after this, after here. So it could take a very long time for original Sanitizer, but you can use attachable Sanitizer and you can just compile it and run it, and long times later you can just attach it and you can get this kind of correct backtrace, which is not, I didn't apply the buzz disappeared patch here, so just unknown, and there should be main, but it's just disappeared, and that is mangled name of operator new. Okay. Okay, let's go to the actual issue. I applied my attachable Sanitizer to JSON project, which is one of the very famous C++ project. And here I just search memory leak problems in this project, and I find two things, and which is already fixed, by the way. So I moved the version right before that patch is applied and generate leak with original LSan, and there will be report, and I apply attachable LSan and compare it, and I will show you that that is same. That's almost same. So first case, this is the output of original Sanitizer, and you can see that there is a directly 32 bytes and long and very long core chain. And I apply attachable Sanitizer and same 32 bytes directly and long backtrace. Yes, it either didn't, yeah. It either didn't apply that missing core chain patch. So here you can see that allocator traits, and it is right. It should be actually it is new allocator, but it in attachable LSan it is showing this one from here. Okay.
So actually, Boost has a name demangler.
Part.
Boost library
Yeah.
has name demangling
Oh.
library. You can use it to
Oh.
demangle the names.
Okay.
Portably.
Okay. Thanks.
You're already non-portable on Linux.
That's what I
Just
was
make an
Yeah,
API.
no, but this yeah, I understand, but this library would work across multiple compilers. Like,
Okay.
I don't know.
That sounds very good. I didn't implement it yet, demangling, so I have to implement it
Yeah,
if I go
you
home.
can use it from Boost library. It's
Oh.
like an utility header, I think.
That's cool, but yeah. In fact, it's implemented in C, so I'm not sure I can use this library, by the way.
That was actually going to be my next question. With the fact that we're doing like the stuff in the kernel, I've heard that there's problems with using C++ in the kernel. Like, is that actually hard restricted for the eBPF program, or maybe that's beyond scope for this talk? I was just curious. But,
There's an LGM backend for eBPF,
And
so
then
you
call
cannot.
C++ count.
I mean, again, I'm just going off of what I heard from a while back. But I.
Okay, we can, yeah.
I would say that there's an LGM backend for eBPF, so you're not running C++, you're running eBPF in the kernel.
Gotcha. Okay.
Okay, move on to the next case. Samely, I run original Sanitizer for this, and I can get 8 bytes of indirect leak and 48 bytes of indirect leak. And I apply Attachable Sanitizer, and here you can see that 8 bytes of indirect leak, and here and 48 bytes of indirect leak as well. Okay, so here's one thing I want to share you a little bit more is how to build it, and this is how. Just clone it and build it, and you can get it. I will upload it to the, you can take a picture anyway. Okay, thanks. Okay.
Do you have to have it attached when the malloc happens in order to get the backtrace where the leak happened?
Sorry, I didn't understand.
Do you have to attach this tool before the allocation happens in order to observe that
Yes,
backtrace?
yes. It is only after you attach. Before one is not just dismissed, cannot trace it. Yeah.
What version of like the Linux kernel? Do you know? Like, I'm not sure what version of Linux eBPF became available in. Do you have any-
It is. I'm not sure, but I'm using this kind of feature from Linux version from 5.4, 5.4 from 5.4. Yeah, and yeah.
You back up the slide once? Like
Once?
Oh, yeah.
There, yeah. Just
Yeah.
leave it there while you're talking.
Ah, okay. I tested on Ubuntu.
One more thing. So you said like you need root privileges. Can one work with capabilities? Maybe there are like capabilities to access memory or something else, not just to give the whole package of root privileges there.
Well, I'm not sure. I didn't try it, but root privilege is needed to. First one is to compile this node and load that eBPF code to kernel that is needing root privilege, and attaching UProof need root privilege, and analyzing phase it is go to the target process memory and it read it, so that 3 paths need root privilege. So
maybe this can be reduced to a bunch of capabilities and not a whole
well,
palette of.
maybe, but I don't think so, because it can be very there can be big security issue can be happen. So I'm not sure, but maybe, yeah.
Yeah, the only other thing I was going to suggest there is that, yeah, like it seems like you would definitely need root privileges to like load the eBPF program to start with, since it's in kernel space. But I guess I'm wondering, like for the utrace call itself, like if you own the process, like if you're trying to trace somebody else's process, it makes sense to me that that would need root privileges.
Yeah.
But if you're tracing your own process, I would assume it's similar to attaching a debugger. Like I guess I don't know for sure, but
I guess that will work. Yeah, you're right. I think you're right. Yeah. Okay, thank you.
yeah.